Hi, my name is Stephan Knapp.
And my name is Darshil Shah.
And we created a pendulum and measured the dampening ratio, natural frequency, and formulated a second-order differential equation to model the system.
We also changed the sampling rate by changing the frames per second and measured the Nyquist frequency and calculated the aliasing frequency.
This is the second-order differential equation we use to model the system. This is that same equation with all the constants plugged in. This is the damped sinusoidal response of the pendulum. These are the peaks we use to calculate delta in order to find the dampening ratio. This is the exponential function used to describe the dampening of the system. We use these equations to calculate delta, the dampening ratio, and the natural frequency. The setup of our pendulum system. What we are measuring here is theta. We're using this to calculate delta. This is our experimental data. This is our measured value of theta. And this is the ratio of theta n over theta n plus 2. This is the ratio of 1 over 3. This is the ratio of 3 over 5. This is the ratio of 5 over 7. And this is the ratio of 7 over 9. And this is the average of those ratios. This is our calculated delta, or dampening ratio, and natural frequency of the pendulum system.
So for the next part of the project, we decided to calculate the aliasing frequency by changing the sampling rate. So first I'm going to try to explain to you what an aliasing frequency is. So let's say you have a sinusoidal function. This is an example where your sampling rate is good enough to represent what your function looks like. You have many data points, and by connecting the data points you can see what the sinusoidal function looks like. But let's say your sampling rate wasn't as high, it was very, very, very low, and your data point that you took were here, 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 and here. If you were to plot that on this graph, you would get a function that looks something like this. Now, this function also fits the data point you have very well. But as you can see, the frequency is not the same. This new frequency that was changed because you didn't take enough data points is called the aliasing frequency. It goes through all the data points, but it is not a good representation of what it actually looks like. So you try to keep the sampling rate to make sure you do not get something like this. thing we did for our system was we calculated the frequency of the system, which we just did by 1 over the period, which we calculated to be 1.7 seconds, which gave us the frequency of 0.588235. Next, we also needed to calculate the Nyquist frequency, which is thus half of the sampling frequency. The sampling frequency we had were 1, 2, 3, 5, 10, 15, 20, 25, and 30 hertz. We had this different sampling frequency by changing frames per second. So 1 hertz was 1 frame per second, 2 frames per second, and 30 frames per second. So to calculate the Nyquist frequency, we just multiply the sampling frequency by half, which gave us a value of 0.51, 1.5, 2.55, 7.5, and all the way to 15. Next, we needed to calculate the ratio of our frequency over our Nyquist frequency. All of those values can be found on this column of data. In order to calculate the aliasing frequency, we must find the constant that we need to multiply our Nyquist frequency by using F over Fn. To do that, we use figure 7.3 in Figliola, which is the folding diagram for aliasing frequency. As you can see, the bottom course line goes from 0 Fn to 1 Fn, and from 1 to 2, 2 to 3, and it continues on. So to calculate the constant, we look at our F over Fn ratio. We find the corresponding value in our folding diagram. For this case, it lies somewhere about here. So in order to get our aliasing frequency, we must find a corresponding value of this on this, and we do that just by going from here to here, which for 1.17 accounts to be 0.83. After we get that value, we multiply our Nyquist frequency by the value we found using our folding diagram and our F over Fn ratio, and for 1 hertz sampling frequency, we get our aliasing frequency to be 0.415 hertz, which means that our real frequency, which is 0.588235, will not be represented by a sampling rate of 1 hertz. If we are to increase our sampling rate to 2 hertz, our F over Fn ratio becomes 0.588235. Now, if you look at the folding diagram, you can see it already lies on this bottom of the chart over here. So we can just take the value that we calculated, the ratio we calculated, and multiply it by our F over N. And as you can see, the aliasing frequency does represent our true frequency. You can see the same thing for sampling rate of 3 hertz, 5 hertz, 10 hertz, 15, all the way to 25. All of these multiplied out will end up giving you 0.588325 hertz, which is the frequency of our pendulum system.